Okay, picture this. A river of molten rock, just glowing, red hot, maybe yellow, carving its way across the land.
Yeah, lava, straight from inside the Earth, incredibly hot.
Right, like 1100, 1200 degrees Celsius hot. And get this, it can move really fast sometimes, like up to 60 kilometers an hour on steep bits.
It's amazing. And then, almost bizarrely, this super hot liquid actually freezes into solid black rock.
It's such a powerful image, isn't it? But the really mind-bending thing is that most of this action, the formation of this stuff, happens way down deep, totally hidden.
Exactly. That's the paradox. We see the dramatic lava flows, the eruptions,
Yeah.
but that's just a tip of the iceberg, really.
So for this deep dive, we're going beyond the surface show.
Yeah, we're diving into the world of magma. That's the underground stuff and the igneous rocks it forms. We'll look at where it comes from, why it moves up, how it solidifies, both above and below ground.
And how we classify these rocks and how it all connects to plate tectonics.
Precisely. We're basically unpacking how a huge part of our planet's crust gets made, using the source material, the core ideas, processes, even the diagrams and geotour examples from the chapter to give you a really solid understanding.
Okay, sounds good. Let's start at the basics then. Magma and lava. We hear both terms. What's the actual difference?
It's fundamentally about location. Magma is the molten rock while it's still beneath the Earth's surface.
Underground, right.
The instant it erupts onto the surface, typically out of a volcanic vent, we switch terms and call it lava.
So eruption is the key moment of change.
Yeah. And that eruption can look very different, right? You can have those incredible lava fountains shooting way up.
Hundreds of meters sometimes.
Or calmer lava lakes pooling in craters, or those flowing rivers we started with. And importantly, the rock that forms when that lava cools is also often called a lava flow, like a sheet of rock.
Okay. But not all eruptions are just flows, are they? Some are
Yeah.
explosive.
Absolutely. Explosive eruptions blast out fragments, shattered bits of existing rock, solidified drops of lava.
Huh.
We call all that stuff pyroclastic debris.
Ah, so that's the ash and coarser stuff in those big eruption clouds.
That's it exactly. Now, when we talk about the rocks that form from all this, we divide them based on where they solidify.
Makes sense.
If it solidifies above ground so, cooled lava, or cemented pyroclastic debris, we call it extrusive igneous rock. Extrusive like exit.
Like those hardened lava flows you mentioned.
Right. But, as we said, most igneous rock actually forms underground. When magma cools and solidifies within existing rock,
That's intrusive?
intrusive igneous rock, yes. And the bodies of this rocks are called igneous intrusions.
Okay, so all this heat, why is it so incredibly hot inside the Earth? It's not just leftover heat from formation, is it?
Well, a lot of it is leftover heat, but it's also continuously generated. Think back to the Earth's formation billions of years ago.
Just dust and gas swirling around.
More like small bodies, planetesimals smashing together. Each collision generated heat, converting kinetic energy.
Right, impact energy.
Then, as the Earth got bigger, gravity compressed everything, squeezing it, which also generates heat. Think like a bicycle pump getting warm.
Okay, compression heating.
And a really big one. When the early Earth got hot enough for heavy elements like iron to melt and sink towards the center to form the core,
Friction.
huge amounts of frictional heat from all that sinking metal. Plus, there was that massive collision with a Mars-sized object, early on a colossal heat input. And even after that, impacts continued for a while.
Wow. So a very violent hot beginning. But that was billions of years ago. Why hasn't it all cooled down?
That's the key ongoing heat production from radioactive decay. Certain elements, isotopes like uranium, thorium, potassium, naturally decay over time.
And that releases energy.
Tiny amounts per atom, but multiply that by the vast amount of these elements within the Earth, especially the crust, and it adds up to a significant continuous heat source.
So it's like a slow-burning internal furnace keeping things warm?
Exactly. It's dramatically slowed down the Earth's cooling. So even today, the base of the rigid outer layer, the lithosphere, is around 1,300 degrees C.
Yeah, in the center.
Over 4,700 degrees Celsius.
Yeah.
Getting close to the sun's surface temperature, which is around 5,700 degrees C.
Incredible. Okay, so it's blazing hot down there. But as you said, most rock is solid. What actually causes it to melt into magma? It seems like it should all be molten.
That's the counterintuitive part, isn't it? It's the immense pressure. Deep inside the Earth, the pressure is so high, it forces the atoms into rigid solid structures, even at very high temperatures.
So pressure prevents melting, usually.
Usually. Melting only happens in specific geological settings where conditions change. There are three main ways this happens. First, decompression. Melting.
Decompression, like reducing pressure.
Exactly. Imagine you have hot mantle rock under huge pressure deep down. If that rock moves upward, say, beneath a rift zone or a mid-ocean ridge, the pressure drops significantly, even if the temperature stays roughly the same.
And that allows it to melt.
Yes. The atoms can move more freely at that lower pressure, transitioning into a liquid state. We see this under mid-ocean ridges, continental rifts, and mantle plumes. It's like lifting the lid on a pressure cooker.
Just taking the squeeze off does it. Wow. Okay, what's the second way?
The second is melting due to the addition of volatiles,
Yeah,
or flux melting.
volatiles. Like water.
Water is a key one, yes, but also carbon dioxide, things that easily become gases. When these substances mix with hot, dry rock, they help break the chemical bonds holding the minerals together.
Like a chemical lubricant.
Sort of, yeah. It effectively lowers the rock's melting temperature. This is really important at subduction zones.
Where one plate goes under another.
Right. The subducting oceanic plate carries water trapped in minerals down into the hot mantle. As it heats up, the water gets released.
And rises into the mantle above.
Exactly. It infiltrates the hot rock overlying the slab and triggers melting by lowering its melting point, like adding salt to ice to make it melt.
Flux melting. Got it. And the third mechanism.
Third one is heat transfer melting. Pretty straightforward, really. If very hot magma from the mantle rises up into the cooler crust,
It brings heat with it.
a lot of heat. It conducts that heat to the surrounding crustal rock, the wall rock. If it heats that wall rock enough, it can start to melt too.
Like the hot fudge melting the ice cream example from the book.
That's the perfect analogy. This happens in various settings, rifts, convergent boundaries, hot spots anywhere. Magma intrudes the crust.
Okay, decompression, flux melting, heat transfer. That covers why it melts. Now, what is this molten rock actually made of? It's not just one thing.
Definitely not. It's a complex chemical soup, a hot liquid mix of many different elements. Geologists usually describe the composition in terms of oxides, elements bonded to oxygen.
Oxides, like rust is iron oxide.
Sort of, yeah. Common ones in magma are silicon dioxide, SiO2, which is the main component of quartz,
And glass.
right? Also aluminum oxide, iron oxides, calcium oxide, magnesium oxide, sodium, potassium oxides, a whole list.
And these are all just sloshing around.
Not quite randomly. They form little clusters and short chains that are constantly moving and breaking apart. It's not the neat, ordered structure you find in a solid crystal. Very dynamic.
And I read about dry versus wet melts. What's that about?
That refers back to those volatiles we mentioned, the dissolved gases.
Water, CO2.
Exactly. Dry melts have very few dissolved volatiles. Wet melts, though, can contain quite a bit, up to maybe 15% by weight. Water is usually the most common one.
And these are the gases that come out of volcanoes.
Precisely. When the magma rises and pressure drops, these volatiles come out of solution and form gas bubbles, driving eruptions. It's amazing to think magma gives us rock, but also contributes water and gases to the oceans and atmosphere.
That connection is really interesting. Now, the source material gets into different compositional types. Mafic, ultramafic, felsic, intermediate. Can you break those down?
Yeah, these are really important categories. They're based on the overall chemistry, especially the amount of silica, SiO2, relative to magnesium oxide, MgO, and iron oxide, FeO or Fe2O3.
Okay, so mafic.
Mafic melts have relatively less silica, maybe 46, 52%, and more magnesium and iron. The name helps. Mafic for magnesium, a fefic related to iron.
And ultramafic.
Even more magnesium and iron, and even less silica, like 38, 45%. Very rich in those elements.
Then felsic is the opposite.
Right. Felsic, or sometimes called silicic, is high in silica, 67, 76%, and lower in magnesium and iron. Think feldspar and silica minerals.
And intermediate is in between.
You got it. Compositionally between mafic and felsic, typically 53, 66% silica. It's basically a spectrum, from silica poor and magnesium rich to silica richer and magnesium poor.
What controls where a melt falls on this spectrum? Is it just the rock it came from?
The source rock composition is definitely the starting point. Melting different rocks gives you different magmas, but other things modify it.
Like what?
A huge one is partial melting. Rocks don't usually melt completely all at once. Typically only a fraction melts, maybe 2% to 30%.
Yeah.
And crucially, the melt that forms first is usually more felsic than the source rock it came from. Silica-rich components tend to melt at lower temperatures.
So if you partially melt an ultramafic rock,
You'd likely get a mafic magma. It's like brewing coffee. The first bit extracted is different from the whole bean.
that makes sense. What else changes the composition?
Assimilation. As magma sits in a chamber, it can melt and incorporate bits of the surrounding wall rock.
Contaminating itself, basically.
Yeah, or contamination. Chunks of wall rock might even break off and sink into the magma, altering its chemistry.
Right.
We call those xenoliths if they don't fully melt.
Foreign rocks inside the magma.
Right. And then there's magma mixing. If two different magmas enter the same chamber, say a felsic one and a mafic one, they can mix.
And create an intermediate one.
Exactly. So the magma's journey from source to solidification can involve quite a few changes to its original recipe.
Fascinating. Okay, so this magma forms deep down, gets modified. Why does it rise? It has to push through solid rock.
Two main reasons. First, buoyancy. Magma is usually less dense than the solid rock around it.
Like a cork in water.
Good analogy. It wants to float upwards. Second is pressure. The sheer weight of overlying rock squeezes the magma, forcing it upwards into any available cracks or zones of weakness.
Like squeezing toothpaste out of a tube?
Sort of, yeah. Pushed from below and buoyant.
Does all magma move at the same speed? Those lava flows we see vary a lot.
They do vary hugely. The key property controlling flow speed is viscosity.
Resistance to flow.
Exactly. Think honey versus water. Magma is always way more viscous than water, but its viscosity varies a lot based on a few things. Temperature is big, hotter melt, lower viscosity.
Our energy flows easier.
Right. Volatile content matters too. More dissolved gases tend to lower viscosity. They help break up the silicate structures.
Okay, and silica content. I remember reading that's critical.
Absolutely critical. Mafic melts with less silica are much less viscous runnier. Felsic melts high in silica are much more viscous, thick, and sticky.
Why does silica make it sticky?
It's down to the silicon-oxygen tetrahedra, the basic building blocks. In felsic melts, these tetrahedra link up easily, forming long, complex chains and networks that tangle up and resist flow.
Ah, like microscopic spaghetti.
Kind of. So hot mafic lava flows easily, spreading out in thin sheets. Cool felsic lava is sluggish. It piles up, forming thick flows or domes near the vent, like in figure 6.8.
That explains the different volcano shapes too, partly. So eventually this moving melt cools and solidifies, freezes back into rock. What triggers that?
Mostly cooling, yeah. As magma rises, it enters cooler regions of the crust, so it loses heat to its surroundings.
Slower underground, faster at the surface.
Generally, yes. Magma trapped underground in an intrusion loses heat slowly to wall rock. Lava erupted to the surface loses heat much faster to the air or water.
Makes sense.
Loss of volatiles can also play a role. Since volatiles lower the melting point, if they escape as gas when pressure decreases near the surface, the remaining melt might solidify even if the temperature hasn't dropped much.
Interesting. So what controls how fast it cools and solidifies?
The rate of heat transfer is key.
Yeah.
Several factors influence that. Depth is one. Deep intrusions, surrounded by hot rock, cool very slowly. Shallow intrusions near the cool surface cool faster.
Okay.
Shape and size matter a lot, too. Think about surface area versus volume, like in figure 6.9a. A thin, pancake-shaped intrusion cools faster than a rounder, melon-shaped one of the same volume, because the pancake has more surface area to lose heat from.
Right, more exposure.
And smaller bodies cool faster than larger bodies of the same shape. Also, circulating groundwater can carry heat away very efficiently, speeding up cooling significantly, as shown in 6.9b.
Like a natural cooling system. Do these same things apply to lava on the surface?
Absolutely. Thin lava flows cool faster than thick ones.
Yeah.
Tiny droplets sprayed out in eruption cool almost instantly because they have huge surface area for their tiny volume.
And lava underwater.
Cools much, much faster than in air. Water is way better at pulling heat away.
Okay. Now, as it's cooling, does it just solidify into one uniform block, or does the composition change during cooling?
This is where it gets really interesting. It undergoes fractional crystallization. It doesn't just freeze uniformly.
Fractional, meaning in parts.
Yes. As the mafic magma cools, specific minerals, usually the ones richer in iron and magnesium, like olivine and pyroxene, crystallize first.
The high-temperature minerals?
Exactly. And these early crystals are often denser than the remaining liquid magma, so they might actually sink down through the melt. This is shown conceptually in figure 6.10.
So they settle out.
They can, yeah. Or they might react with the remaining melt or just get isolated. But the key point is, this process preferentially removes iron and magnesium from the liquid,
Leaving the remaining liquid.
richer in silica, becoming progressively more felsic as cooling continues.
So one starting magma can produce different rocks depending on how much of this happens.
Precisely. If it freezes early, you get a mafic rock. If fractional crystallization goes on for a long time, removing lots of mafic components, the very last bit of melt to solidify can be quite felsic.
Wow, that explains a lot of the diversity. And this sequence, this order of crystallization. That's Bowen's reaction series, right? Box 6.1 in the text.
That's exactly it.
Yeah.
N.L. Bowen did groundbreaking lab work in the early 20th century, figuring out this precise sequence. It's fundamental.
Can you give us the quick version? It looks a bit complex in the diagram. BX 6.1.
Sure. Bowen found two main pathways as a mafic magma cools. There's a discontinuous series where one mineral type reacts with the melt to form the next mineral type in the sequence. It goes olivine first, then pyroxene, then amphibole, then volatile mica.
Different mineral groups, one after another.
Right. Then there's a continuous series happening simultaneously, involving plagioplase feldspar. It starts crystallizing as a calcium-rich version at high temperatures and continuously changes composition to become more sodium-rich as the temperature drops.
Same mineral, just changing its recipe.
Exactly. And finally, any remaining melt, now very silica-rich,
Yeah.
crystallizes potassium feldspar, muscovite mica, and quartz at the lowest temperatures.
So the minerals that form later are more silica-rich.
Generally, yes, especially in the discontinuous series. They also have more complex silicate structures. It provides a roadmap for understanding why certain minerals tend to occur together in igneous rocks.
Okay, that's a powerful concept. Now let's link this back to the settings. Extrusive versus intrusive. How do they differ in the rocks and features we actually see?
Extrusive setting surface eruptions are really diverse, mainly because lava viscosity and gas content varies so much.
Right, runny mafic versus sticky felsic.
Exactly. Low viscosity mafic lava makes those broad, thin flows like we see in Hawaii or historically around Vesuvius, as shown in figure 6.101A and C.
Spreading out easily.
Whereas viscous, often felsic lava, if it's low on gas, just piles up into steep mounds called lava domes.
Too sticky to flow far.
Right. And if lava is rich in volatiles, especially felsic lava, you get explosive eruptions. That produces pyroclastic debris ash, lapilli, pea to golf ball size, bombs.
Stuff that makes tough and breccia.
Yes. And dangerous pyroclastic flows, those fast, hot avalanches of ash and gas, shown in 6.11b, D, and E. The New Mexico ash deposits are from flows like that. The Izalco volcano geotour is a good example, showing lava flows of different ages.
Okay, so extrusive is all about surface flows and explosions. What about the hidden intrusive world?
Intrusive settings are where magma pushes into existing rock underground and freezes there. The boundary is the intrusive contact. The shapes vary a lot.
Like sheets and blobs.
Pretty much. Tabular or sheet intrusions are relatively thin but can be extensive. A dike cuts across the layering in the surrounding rock, like in figure 6.1N and 6.13A. Think shiprocks dikes. Dikes often form when the crust is stretched.
Big 6.16A.
Like vertical walls of magma.
Yeah. A sill, though, injects between the layers, parallel to them, like spreading a layer cake. Using 6.116b, the Antarctic sills and sandstone, 6.12c, are a classic example.
So dikes cut across, sills squeeze between.
Right, and if magma pushing between layers gets blocked or is too viscous, it can bulge upwards into a blister shape called a laccolith, doming the rock above and the bigger irregular ones.
Those are plutons. Irregular, blob-shaped intrusions, maybe tens of meters to tens of kilometers across.
Just big masses of solidified magma.
Exactly. And when you get lots and lots of plutons intruded close together in one region, they form a massive composite body called a batholith. These can be huge, hundreds of kilometers long.
Yeah, like the Sierra Nevada.
Yes. The Sierra Nevada batholith is a prime example, beautifully exposed in places like Yosemite Half Dome Geotour 6.15.
These things are enormous. How does the Earth make space for them down there? The rock has to go somewhere.
That's a great question and still an area of active research. For dikes and sills, it's often related to crustal stretching, opening cracks, dikes, or magna pressure lifting overlying rocks near the surface cells.
Okay, that makes sense for the sheet-like ones, but giant plutons.
More complex. One idea is diapers, buoyant, bubble-like masses of magma rising and shouldering aside the surrounding rock.
Pushing their way up.
Pushing their way up. Another process is stopping. Magma can break off blocks of the surrounding wall rock, which then sink into the magma chamber. Those are the xenoliths we mentioned.
So it eats its way upwards.
In a way, yes, incorporating the surrounding rock. A newer idea suggests some plutons might actually build up from many smaller, overlapping injections of dikes and sills over time, rather than being one giant blob.
A combination of processes, maybe?
Probably. Often helped by regional tectonics creating space through stretching or uplift and erosion removing overlying rock.
Which brings us to how we even see these things. They form deep underground.
Right. Mountain building lifts the crust up, and then erosion water, wind, ice strips away the overlying rock over millions of years, eventually exposing these deep-formed intrusive rocks at the surface.
So when we see granite mountains, we're looking at the ancient roots of magma chambers.
Often, yes. like looking deep into the plumbing system of past geological events.
Okay, so let's say we find one of these rocks, intrusive or extrusive. How do geologists actually describe and classify it, like that granite countertop?
Ah, yes, the countertop granite. That term gets used very broadly in construction for almost any hard crystalline rock. Geologically, granite is more specific.
So what do geologists look at first?
We start with color and texture. Color gives clues overall light or dark. Specific shades like pink, gray, black. It often relates to composition, felsic light, mafic dark, dark. But grain size and tiny impurities can affect it too.
And texture, that's about the grains or crystals.
Exactly. Texture describes how the components are arranged, and it tells you a lot about how the rock formed, especially cooling rate.
What are the main texture types?
We broadly group them. Crystalline textures have interlocking mineral crystals, like a jigsaw puzzle. This usually means it cooled slowly enough for crystals to grow.
Okay.
Within crystalline, we look at crystal size. Coarse-grained, or phaneritic, means crystals are big enough to see easily with the naked eye. That indicates slow cooling, deep underground, typical of plutons.
Like granite.
Yes. Fine-grained, or aphanitic, means the crystals are too small to see without magnification. That implies rapid cooling, typical of lava flows, or small intrusions like dikes and sills.
Like basalt.
Basalt is a perfect example. Then there's porphyritic texture, large crystals called phenocrysts, embedded in a fine-grained matrix, the ground mass.
A mix of sizes.
Right. It usually indicates two stages of cooling. Slow cooling first, growing the big phenocrysts, then faster cooling, forming the fine ground mass, often because the magma erupted.
So texture really is a cooling speed indicator. What about non-crystalline textures?
Good point. There's fragmental texture, Fig 6.1ab, that's rocks made of broken pieces, pyroclastic debris packed or welded together. Think volcanic ash layers turning into rock. Size of the fragments is key here.
Like tuff or volcanic breccia.
Exactly. And then there's glassy texture, Fig 6.18c. This is essentially rock that cooled so fast the atoms couldn't arrange into crystals at all. It's amorphous solid, like window glass. Obsidian is the classic example. Often breaks with that characteristic curved conchoidal fracture.
So slow cooling big crystals, fast cooling small crystals, super fast cooling glass. Any exceptions?
One main one, pegmatite. These are igneous rocks, often in dikes, with exceptionally large crystals, sometimes huge.
But dikes usually cool quickly.
They do. The secret with the pegmatites is that they form from melts, very rich in water and other volatiles. These volatiles make the melt less viscous and, crucially, allow atoms to move around much faster.
So crystals can grow big even if it cools relatively fast.
Exactly. High diffusion rates overcome the faster cooling rate.
Fascinating. Okay, so using texture, cooling rate, and composition, mineral content,
Okay.
how do we actually classify specific rocks? The geology at a glance chart on page 178 seems key here.
It is. For crystalline rocks, the 6.1 metal, we basically use a grid. Composition, ultramafic, mafic, intermediate to felsic on one axis, grain size, coarse or fine, on the other.
Give me some examples again.
Sure. Coarse grain mafic is gabbro, fine grain mafic is basalt, coarse intermediate is diorite, fine intermediate is andesite, coarse felsic is granite, fine felsic is rhyolite,
And ultramafic.
coarse is peridotite. Fine-grained ultramafics like comatite exist but are rare at the surface today. Color helps too, as a rough guide. Mafic, dark, felsic light.
Okay, that covers the crystalline majority. What about the glassy ones?
Classified mainly by appearance and vesicles, glass bubbles trapped during cooling. Obsidian is dense, glassy, felsic rock. Tachyllite is rare mafic glass.
And the bubbly ones?
Pumice, felsic glass foam, supervesicular, very light, often floats. Scoria, 6.21b, is mafic, also vesicular but generally denser, with larger bubbles, looks cindery.
Got it. And the fragmental rocks?
Classified by fragment size. Tough, Buck 6.21c, is rock made of fine ash, maybe with some lapilli. If it was hot enough to fuse, it's welded tough.
And bigger fragments?
Volcanic agglomerate is made of lapilli, or larger bombs. Volcanic breccia is composed of angular fragments cemented together. There's also hyaloclastite, a breccia formed when lava hits water or ice and shatters.
So texture and composition really are the keys to unlocking the rock's history. Now let's put it all together on a global scale. How does this all tie into plate tectonics? Where does most igneous activity happen?
Fig 6.22 shows the map.
The link is incredibly strong. Most igneous activity is concentrated along specific plate boundaries. You see it intensely at volcanic arcs above subduction zones, convergent boundaries.
Like the Ring of Fire.
Exactly. Also, huge amounts along mid-ocean ridges where plates diverge, and in continental rifts where continents are pulling apart, plus those isolated hotspots. Plate tectonics really drives the whole melting process.
Okay, let's break those down. Convergent boundaries, first subduction zones. Figure 6.23, 6.24. What happens there? You get volcanic arcs, chains of volcanoes on the overriding plate. If ocean crust subducts under a continent, you get a continental arc like the Andes or Cascades, lots of granite intrusions deep down, and andesite felsic eruptions.
Andesite named after the Andes. Makes sense.
And if ocean crust subducts under other ocean crust, you get a volcanic island arc, like the Aleutians or Marianas. The Aleutian geotour shows this well. Lots of basalt and andesite, plus intrusions forming the island's core.
What's the melting mechanism here again?
Flux melting. The subducting oceanic plate carries water down. Around 150 kilometers deep, the heat forces that water out of the minerals
The water rises.
into the hotter mantle wedge above the slab. This lowers the mantle's melting point, generating basaltic magma.
Okay.
Some of that erupts directly. In continental arcs, some basaltic magma gets trapped in the thick crust, cools fractionally, becoming more felsic, and transfers heat, melting the continental crust itself to produce intermediate to felsic magmas.
So a multi-stage process in continental arcs. What about mid-ocean ridges, divergent boundaries? You said most activity is there.
By volume, yes, it's where all the oceanic crust is made, hidden underwater, mostly. The entire 710-kilometer thick crust of basalt and gabbro forms here.
How does melting happen there?
Decompression melting. As plates pull apart, hot asthenosphere rises to fill the gap. Pressure drops, it partially melts, producing basaltic magma.
Which forms the new crust.
Right, it collects in shallow magma chambers. Slow cooling at the edges forms gabbro, lower crust. Some rises further. Some injects as basalt dikes, middle crust, and some erupts as pillow basalt onto the seafloor, upper crust. The cypress-ophiolite shows this structure on land.
An amazing seafloor factory. What about continental rifts, like East Africa?
Similar process to ridges, but under a continent. Stretching thins the lithosphere, causing decompression melting below, making basaltic magma.
So basalt eruptions.
Yes, slows and intrusions, but also that hot basaltic magma can heat and melt the continental crust above it.
Leading to felsic melts?
Exactly, often resulting in explosive rhyolite eruptions and ash deposits. So rifts often have both basalt flows and rhyolitic rocks.
A mix of melt types. Okay, last setting. Hotspots, like Hawaii or Yellowstone. Not on plate edges.
Often not, though some are near boundaries, like Iceland. They're thought to be fed by mantle plumes, columns of extra hot rock rising from deep in the mantle.
The plume itself isn't magma.
No, it's solid rock, just very hot. When the hot plume head reaches the base of the lithosphere, decompression melting happens, generating mafic magma.
So basalt at oceanic hotspots like Hawaii?
Mostly, yes, building huge shield volcanoes.
Right.
At continental hotspots like Yellowstone, you get basalt too. But again, that rising magma heats the thick continental crust, causing melting and generating those big felsic rhyolite eruptions Yellowstone is famous for.
Yellowstone's ash layers are volcanic, rhyolitic.
Huge rhyolite eruptions, yes. Fueling the geysers and hot springs, too.
And one more thing mentioned. Large igneous provinces, LIP, 6.6Ts, what are there?
LIPs are just enormous outpourings of magma. Mostly mafic, erupted or intruded in a geologically short time.
Yeah.
Way bigger than typical volcanism.
Example.
The Ontong-Java Plateau in the Pacific, oceanic. On land, the Columbia River Flood Basalt's Palouse Canyon Geotour covers this. The Paranal basalts in South America, Iguazu flows over them, Deccan traps in India, Karoo in South Africa.
What causes such huge events?
Often linked to the arrival of a mantle plume head at the base of the lithosphere. The plume head is much larger than the tail, causing way more melting.
A massive initial burst of magma.
Potentially, yes.
Yeah.
If the overlying lithosphere is also stretching, these huge volumes of runny basaltic lava can erupt as flood basalts, covering vast areas. They're major events in Earth history, maybe linked to superplumes.
Incredible scale. Okay, I think we've covered the ground outlined in the chapter.
I think so too. So just to recap this deep dive, we started with magma and lava, understanding their molten rock, differing mainly by location. We saw melt forms through decompression, adding volatiles or heat transfer.
And its composition, mafic, felsic, etc., depends on the source rock, but also gets changed by partial melting, assimilation, and magma mixing.
Right. Then we looked at why magma rises buoyancy and pressure, and how viscosity, controlled by temp, volatiles, and especially silica, dictates how it flows.
Then solidification. Cooling is key, but fractional crystallization and Bowen's reaction series show it's a complex process creating different minerals and rock types from one initial melt.
We compared extrusive settings, lava flows, domes, pyroclastics with intrusive settings forming dikes, sills, laccoliths, plutons, and huge batholiths underground.
and discussed how we describe these rocks using color and especially texture crystalline. Coarse, fine, porphyritic, fragmental, glassy, which tells us about cooling history.
Leading to the classification system based on texture and composition, gabbro basalt, diorite andesite, granite or hyalite, plus glassy types like obsidian, pumice, scoria, and fragmental ones like tuff and breccia.
And finally, we tied it all into plate tectonics. Subduction zones, flux melting, mid-ocean ridges and rifts, decompression melting, hot spots, plumes and decompression heat transfer, and those massive LIPs. We've really journeyed through the whole life cycle.
We have. We've hit the core geology ideas, the key processes, implicitly covered the significance of diagrams like Bowen series or intrusion shapes, touched on the geotour examples like Yosemite or Izalco, and discussed how understanding these rocks applies to interpreting Earth's history.
So now, when you encounter these rocks, whether it's the granite bedrock underfoot, maybe like at Elephant Rocks in Missouri, or you see news about volcanic eruptions in Hawaii, or visit geological wonders like the Columbia River Plateau.
You have a much deeper appreciation for the incredible journey that molten rock took deep inside the Earth and maybe dramatically onto the surface to become the solid ground we see today.
Definitely. It provides a whole new lens for viewing the landscape.
Absolutely.
Yeah.
And maybe a final thought to leave you with. Think about the sheer immense volume of igneous rock created and recycled constantly by plate tectonics. How might big changes in plate movements over Earth's history have dramatically altered not just the continents and oceans, but even the atmosphere, considering all the volatiles released by magma?
A reminder of just how dynamic our planet really is, constantly churning and changing, driven by this internal heat engine.
Exactly. A continuous geological cycle shaping everything we see.